I'm going to do section 8. Now we're being recorded. Section 8.4, which is hypothesis testing of standard deviation. My iPad's going all over the place, so let's do it. Hey, look at this. Last section in this chapter, there's only one more left. Okay, so when we're doing standard deviation, if you think of confidence intervals, when I see that, I know I'm thinking of chi-squared, because that's going to be involved in our test statistic. Yeah, that's what we're doing. Okay. Sample size we need, because you know we're going to need degrees of freedom. We need this because that's from our data. Population standard deviation, that's going to be from our null hypothesis, sigma equals something. And to be honest, we don't use the other two. Okay, SRS, and this is strict, so I'm going to show you how we will test for that in this class. And because I either say this is either stated that it's a normal distribution, or we check it, and in this case we're going to check it with a problem in this section. That's our test statistic. It looks a lot like confidence interval, because when we did confidence intervals, we had, this was bounded there, so there's one on the left as well. But notice with a little bit of algebra, they moved the chi-squared up, sigma down. That's our test statistic. That's the formula we're going to use. Since these are all the same, the one I'm going to do is not that one, not this one. I'll do the critical value method just like we did for proportion and for mean. Okay, this diagram. So we'll be looking at a one-tail test here if H1 is sigma greater than some value. Left tail test, H1 sigma less than some value. Two-tail test would be H1 sigma not equal to some value. And then we would need a over here chi-squared left, over here chi-squared right in all scenarios. So if it's this, we need a chi-squared right. If it's this, we need a chi-squared left. If it's this, two-tail test, we need both of them. Okay, here's our problem. Author does not give the standard deviation soon enough. So this is from the data. N is 16. So let's start the analysis for this problem by pulling out the hypotheses. Okay, I've got alpha. Claim that supermodels have heights with a standard deviation. Ooh, as soon as I see that, chi-squared, because this is our claim that is less than sigma equals 7.5 centimeters. That gives me this. Immediately, I'm thinking left tail test, I'm going to need a chi-squared left. My null hypothesis is then equal to, because it's always equal to. So we started our analysis, kind of have the diagram already drawn, but I wanted to do this. I made a dot plot because I wanted to test the normality of my data. Because it's a stringent requirement and it's a little bit skewed left. So that's why I'm saying I would question our results. It's not quite perfectly normal. It's too bad we don't have some out here. Then I'd have a nice normal curve and I'd feel really good. But we're skewed a little bit to the left. Okay, so here's where we stand. I have my level of significance. I know n, I know degrees of freedom, I have my hypotheses. So what I need is my diagram to finish my analysis. It's skewed, left tail test. I need a chi-squared left, area in one tail, so alpha is 0.01. I think a chi-squared, I want the area to the right, which is 0.99. So let's take a sojourn over to our Triola formulas. Hang on, I'm zipping down. Ooh, chi-squared. Okay, area to the right. Well, I don't know why I zoomed out. I've got my column. There's my area to the right. My degrees of freedom is 15. There's my chi-squared left, 5.229. So let's go back and finish our analysis. 5.229. Okay, I need my chi-squared. I need my test statistic. I always put a little t to remind me I'm doing the test. Degrees of freedom squared, s squared over sigma squared. Okay, this is 15. This is 1.84 divided by, we think it's 7.5. That's our null hypothesis. So let's do our calculator on this. And absolutely, I screwed this up because you're telling me, wait a minute, why is that in there? One of these times, I'll do one of these without making a mistake. Now do your calculator. I got 0.901. So where does that fall? Remember, chi-squareds go from 0 and get bigger. So it's way over here. That's our region where we're going to reject H naught. So all we have to do now is finish our conclusion. I had a hunch we were going to do this anyway, because look at our S from our data. That is so far away from the normal population. So it looks like the supermodels, their standard deviation of their height doesn't vary so much. That's saying that they're all relatively tall. So what's our conclusion? Let's scroll down. We reject H naught. our evidence supports the claim that supermodels have a standard deviation of their height that is less than the population of 7.5 centimeters. So since we rejected H naught, we've got pretty good evidence that says supermodels, their height doesn't range that much. So they're all relatively within the same height, whereas the normal population or regular population, it's going to vary a lot more. So that's pretty much this section. This just reiterates what we did. Hey, there's not a squared there. So we're doing okay. And yeah, there we go. This just reiterates everything we did. And we reject it. There you go. There's our conclusion. And that is this section. And that's done with hypothesis testing of one population. I have no idea why this is always the hard part to do. There we go. See you tomorrow or Thursday.